All right, we just did example 9 in the last video where we evaluated the limit as x approaches either positive or negative infinity by looking at horizontal asymptotes. If we know we're approaching positive or negative infinity, going really far out to the left or really far out to the right, if we can find a horizontal asymptote, then we know that our graph's going to get kind of stuck at that horizontal asymptote, and that's what my limit's going to be. But there's a second way of doing these types of problems that's a little more algebraic and using our calculus rules for limits. Let me show you. Limits at infinity. There is an idea or a rule that says that if I have the limit as x approaches infinity and I have a 1 in my numerator, and that numerator is always going to stay that constant, but my denominator is going to be x to a certain power. And as x gets bigger and bigger and bigger as it approaches infinity, what really happens with my fraction? Well, that's kind of like saying if I have 1 over 100 squared, and then I go to 1 over 1,000 squared, and then I go to 1 over 10,000 squared. Isn't that fraction because the denominator's getting really big, but my numerator's staying a 1? Aren't those fractions actually getting smaller and smaller and smaller until eventually they approach 0, right? Same idea if we were going to negative infinity. Even if the bottom is negative and it's really big, my fraction is still a really small number that approaches 0. 1 divided by negative 1,000, 1 divided by a negative 10,000. It's going to approach 0. So anytime I have that, I can say that my limit approaches 0. So we can actually do these same problems the second way and get the same answers as before. And so you can actually decide which way you like best, in my class anyway, just making sure that you at least show me your work on your exam so I know exactly how you're getting those answers, okay? So let's go back and go through example number 9 one more time, but do it using that idea, okay? So here's example number 9a. Remember before we looked at the p's and q's and we got that the limit is 8/3. So we should get the same thing as before, but we're going to do it the second way. So we're going to take this problem, the limit as x approaches infinity of 8x plus 6 over 3x minus 1. And what we're going to actually do is we're going to multiply both the numerator and denominator by 1 over x. And I'm allowed to do that because as long as I multiply the top and the bottom by the same amount, I'm really just multiplying it by 1 because it's the same quantity. So I haven't really changed the value of my problem. Now what I'm going to do is I'm going to distribute this 1 over x to both of my terms in the numerator and the denominator. What ends up actually happening is I'm dividing each term by x. And I chose x because it is the term on the denominator with the highest degree. So that's how you know what you're going to divide by. You're going to divide every single term by the, how do I say this? Every single term in your numerator and denominator by the highest degree of your x that's in your denominator. So in this case, my highest degree in my denominator was an x, so I'm going to divide everything by an x, okay? What that allows me to do then is reduce some of these terms. So 8x over x reduces to just an 8. Now the 6 over x doesn't reduce, so I end up still having a 6 over x. The 3x over x though, the x is reduced and I just have a 3, and then I have minus 1 over x. Now remember our rules for limits is that we should be able to, instead of doing this whole big old chunky problem, do the pieces individually. So I can actually take this now, and I have the 8, or I can say that I have the limit as x approaches infinity of 8, but since there is no x, it's always going to be an 8. And then I can apply the limit to the 6 over x, I can apply the limit to the 3, and I can apply the limit as x approaches infinity to the 1 over x. The 8, again, is always going to stay an 8. There is no varying variable there that's going to change. The 3 is always going to be a 3, so that's why those are still there. But now if I look at this piece, the limit as x approaches infinity of 6 over x. If you notice, my top is always going to be a 6. My numerator is never going to change. But as x gets bigger and bigger and bigger and bigger as it approaches infinity, that means my denominator on that fraction is going to get really big. If my top stays a 6 and my bottom gets really big, we eventually approach 0, right? The rule that we just talked about, where if we have a constant over a denominator that gets bigger, it's going to approach 0. So that part actually zeroes out, and so really in my numerator, I have 8 plus 0. In my denominator, the same thing happens. If I have the limit as x approaches infinity of 1 over x, My numerator is always a 1, but my denominator gets bigger, 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 bigger. So really my fraction approaches 0. So in my denominator, I have a 3 minus 0, or just a 3. So eventually, my top is just an 8, my bottom is just a 3, and I end up getting the limit as 8/3. The same thing that we got when we looked at our P's and Q's, the degree of our top versus the degree of our bottom, and we found that horizontal asymptote. A little bit more work, so you might like the other way better, but technically that's the way that we use our calculus and our calculus rules to find limits at infinity. So do the same thing with B. Let's take B and let's go through and divide every single term by the highest degree x in the denominator. You notice on this one that my highest degree x in the denominator is now an x cubed. So I'm going to go through and divide every single term by x cubed. I'm going to reduce, and I'm going to apply my limits. When I apply my limit as x approaches infinity to 3 over x squared, my top's going to stay a 3, but my bottom's going to get really, 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 really big. Doesn't that eventually approach 0? I'm going to apply the limit to my 2 over x cubed. My top stays a 2. As x approaches infinity, my bottom gets really big and I end up going to 0. So on the numerator, I really have 0 plus 0. On the denominator, I can't really plug in an x there. That 4 is just going to stay a 4. But when I plug in an infinity here, once my bottom gets really big, but my top stays a 1, that's also going to approach 0. So really, on my top, I have 0 plus 0. On the bottom, I have 4 minus 0, which is 4. Well, what is 0 divided by 4? Well, just 0. And isn't that what we got last time when we looked at our P's and Q's? All right, last two, using this new method so we can make sure it works the same as looking at our horizontal asymptotes. On C, I'm going to go ahead and divide everything by the highest degree of my denominator, so in this case it would be an x. I'm going to go through and divide every single term by x. I'm going to reduce, and I'm going to apply my limit rule. When I apply my limit rule here, 3 times infinity, isn't that just going to be a really big number? If I apply my limit rule here, the limit as x approaches infinity of 2 over x, my top stays a 2, my bottom gets big. That means eventually this term is going to approach 0. So on the top, I really have infinity plus 0. On the bottom, I have a 4. He's going to stay a 4. And then this 3 over x, the top stays a 3, the bottom gets really big, so that means that fraction approaches 0. So on the top, I have infinity plus 0, which is infinity. On the bottom, I have 4 minus 0, which is 4. And what's infinity divided by 4? And as that top number grows, the bottom stays a 4. Isn't it just going to go to infinity? And I think that's what we got when we did it the last time, looking at our P's and Q's. You could double check. All right, last one. Let's go through and divide everything in this one by what? What's the highest degree x in the denominator? Looks like an x squared. So pause the video, divide every single term by an x squared, reduce, and then kind of apply your limit rules. What happens when x approaches infinity? And see what you get. All right, after I divided every single term by x squared, and then I reduced, I ended up with a 5 minus 4x over 3 plus 2 over x minus 1 over x squared. As I apply my limit rules here, this stays a 5. As I apply my limit rule here, negative 4 times infinity is really just an infinity. So on the top, don't I just have a 5 minus an infinity? On the bottom, this is going to stay a 3. This is going to go approach 0. And then my last term, 1 over x squared, as my bottom gets big, but my top stays a 1, it's also going to approach 0. So it looks like on the top I have 5 minus infinity. Well, 5 minus a really, 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 really big number is a negative big number, right? 5 minus infinity is really a negative infinity. On the bottom, I have a 3 plus a 0 minus a 0, which is 3. Well, negative infinity divided by 3 is still just negative infinity. And I think that's what we got when we did it last time. Now, if that problem changed and we were doing the limit as x approaches negative infinity, plug in a negative infinity and see how it would change. We should still get the same answer that we got last time of positive infinity. So 2 different ways of doing these limit problems as we approach infinity, whether that's positive infinity or negative infinity. You can look at horizontal asymptotes with your P's and Q's. Just show me what you're doing. Or you can divide every single term by the highest degree x of your denominator and show me that you're using your limit rules